The accurate reckoning for inquiring into all things. The Rhind Papyrus. In context, key civilization, ancient Egyptians, circa 1650 BC. Field arithmetic. Before, circa 2480 BC, stone carvings record flood levels in the River Nile measured in cubits about 20.5 inches and palms about 3 inches. Circa 1800 BC, the Moscow Papyrus provides solutions to 25 mathematical problems, including the calculation of the surface area of a hemisphere and the volume of a pyramid. After, circa 1300 BC, the Rhind Papyrus is produced. It shows that ancient Egyptians used quadratic equations. 6th century BC, the Greek scientist Thales travels to Egypt and studies mathematical theories. The Rhind Papyrus in the British Museum in London provides an intriguing account of mathematics in ancient Egypt. Named after Scottish antiquarian Alexander Henry Rhind, who purchased the papyrus in Egypt in 1858, it was copied from earlier documents by a scribe, Ahmose, more than 3,500 years ago. It measures 12.5 by 78.5 and includes 84 problems concerned with arithmetic, algebra, geometry, and measurement. The problems recorded in this and other ancient Egyptian artifacts, such as the earlier Moscow Papyrus, illustrate techniques for working out areas, proportions, and volumes. Pictured here, the Eye of Horus, an Egyptian god, was the symbol of power and protection. Parts of it were also used to denote fractions whose denominators were powers of 2. The eyeball, for example, represents a quarter, while the eyebrow is 1/8. Representing concepts. The Egyptian number system was the first decimal system. Used strokes for single digits and a different symbol for each power of 10. The symbols were then repeated to create other numbers. A fraction was shown as a number with a dot above it. The Egyptian concept of a fraction was closest to a unit fraction, that is, 1 over n, where n is a whole number. When a fraction is doubled, it had to be rewritten as one unit fraction added to a unit fraction. For example, 2/3 in modern notation would be 1/4 to 1/6 in Egyptian notation, not 1/3 or 1/3 because the Egyptians did not allow repeats of the same fraction. The 84 problems in the Rhind Papyrus illustrate the mathematical methods in common use in ancient Egypt. Project 24, for example, asks what quantity if added to its seventh part becomes 19. This translates as x plus x over 7 equals 19. The approach applied to problem 24 is known as a false position. This technique, used well into the Middle Ages, is based on trial and improvement, choosing the simplest or false value for a variable and adjusting the value using a scaling factor, the required quantity divided by the result. In the workings for problem 24, 1/7 is the easiest to find for number 7, so 7 is first used as a false value for the variable. The result of the calculation 7 plus 7 over 7, or 1, is 8, not 19, so scaling factor is needed. To find how far the guess of 7 is from the required quantity, 19 is divided by 8, the false answer. This produces a result of 2 plus 1/4 plus 1/8, not 2 3 over 8, as Egyptian multiplication was based on doubling and halving fractions, which is the scaling factor that should be applied. So 7, the original false value, is multiplied by 2 plus 1/4 plus an 8, the scaling factor, to give the quantity of 16 plus half over 1/8, or 16 divided by 5/8. Many problems in the papyrus deal with working out shares of commodities or land. Problem 41 asks for the volume of a cylindrical store with a diameter of 9 cubits and a height of 10 cubits. The method finds the area of a square whose side length is 8/9 of the diameter, then multiplies this by the height. The figure of 8 ninths is used as an approximation for the proportion of the area of a square that would be taken up by a circle if it were drawn within the square. The method is used in problem 50 to find the area of a circle. Subtract 1/9 from the diameter of the circle and find the area of the square with the resulting side length. Pictured here, ancient Egyptians used vertical lines to denote numbers 1 to 9. Powers of 10, particularly those inscribed on stone, were depicted as hieroglyphs and picture symbols. Level of accuracy. Since the ancient Greeks, the area of a circle has been found by multiplying the square of its radius, r squared, with the number pi, 3.14, written as pi squared. The ancient Egyptians had no concept of pi, but the calculations in the Rhind Papyrus showed that they were close to its value. The circle and area calculation, with the circle diameter as twice the radius, 2 times r, can be expressed as 8/9 times 2r squared, which simplified as 256 over 8 r squared times r squared, giving an equivalent of pi of 256 over 8. As a decimal, this is about 0.6% greater than the true value of pi. Instruction books. Pictured above, the Rhind Papyrus scribe used a hieratic system of writing numerals. This cursive style was more compact and practical in drawing complex hieroglyphs. The Rhind and Moscow papyri are the most complete mathematical documents to survive the height of the ancient civilization. They were painstakingly copied by scribes well versed in arithmetic, geometry, and mensuration, the study of measurements, and are likely to have been used for the training of other scribes. Although they captured probably the most advanced mathematical knowledge of the time, they weren't seen as works of scholarship. Instead, they were instruction manuals for use in trade, accounting, construction, and other activities that involved measurement and calculation. Egyptian engineers, for example, used mathematics in the building of pyramids. The Rhind Papyrus includes a calculation for the slope of a pyramid using the second, a measure for the horizontal distance traveled by a slope for each drop of a cubit. The steeper side of the pyramid, the fewer the seconds.